All living cells have a membrane potential, which is a voltage difference between the fluid inside of a cell and the fluid surrounding the cell. The membrane potential is called Vm. When a cell is at rest, meaning that it is not generating an action potential, the membrane potential is referred to as the resting membrane potential, or Vrest. The topic of this video is the Goldman-Hodgkin-Katz equation, which can be used to calculate the resting membrane potential of a cell. Before we dive into the equation, there is some background information we need to go over. The resting membrane potential of all living cells is negative, but it can vary quite a bit between different cell types. For example, the resting membrane potential of a glial cell, a cell that provides support for neurons, is about negative 90 millivolts. In contrast, the resting membrane potential of a neuron is about negative 65 millivolts. What accounts for this difference in the resting membrane potential between different cell types? We will see that one major factor that determines a cell's resting membrane potential is the permeability of its membrane to different types of ions. We will first consider glial cells. To calculate the resting membrane potential of a glial cell, we will make the simplifying assumption that the membrane is only permeable to potassium. This isn't completely true, but will make our calculation much easier. In most mammalian cells, the concentration of both potassium and chloride ions is higher inside of a cell compared to outside. In this diagram, individual potassium ions are represented by red squares, and individual chloride ions are represented by purple circles. The permeability of the cell membrane to potassium is due to the presence of ion channels for potassium. By moving through channels, potassium ions are able to move down their concentration gradient from inside of the cell to the outside. Note that chloride ions are not able to move down their concentration gradient due to the lack of chloride channels. The movement of a potassium channel, which has a large charge of +1, leads to a charge imbalance across the cell membrane. For each potassium ion that moves outward, the inside of the cell becomes negative with respect to the outside. The movement of potassium ions leads to the generation of a voltage difference across the membrane. The end result of the movement of a small fraction of the intracellular potassium ions across the cell membrane is that the inside of the cell becomes negative with respect to the outside. This voltage difference is sometimes referred to as an electrical gradient because, like a chemical gradient, it can affect the movement of an ion. An ion moves down its chemical gradient from an area of high concentration to an area of low concentration. An ion also moves down its electrical gradient. For example, in an electrical field, a positive ion moves from an electrically positive region towards an electrically negative region. The voltage across a membrane that perfectly counteracts the effect of an ion's chemical gradient is called the equilibrium potential. At this potential, there is no net movement of the ion across the membrane. For example, for a given ratio of extracellular to intracellular potassium, there is an equilibrium potential that results in no net movement of potassium ions across the membrane. The equilibrium potential of an ion can be calculated with the Nernst equation. Shown here is a version of the Nernst equation that is correct for a temperature of 37 degrees Celsius, which is the normal core body temperature of a mammal. The equilibrium potential of an ion, E ion in millivolts, equals 61.5 divided by Z multiplied by log base 10 of the ion concentration outside divided by the ion concentration inside, where Z is the electrical charge of the ion. For example, Z is 1 for potassium, which is monovalent and has a positive charge. In the case of potassium, we can simplify the equation. The equilibrium potential of potassium, EK in millivolts, equals 61.5 multiplied by log base 10 of the ion concentration outside divided by the ion concentration inside. Let's try out this equation by plugging in values for the concentration of potassium inside and outside of a glial cell. The extracellular potassium concentration of a mammalian cell is about 5 millimoles per liter, and the intracellular concentration is about 150 millimoles per liter. Thus, EK equals 61.5 multiplied by log base 10 of 5 divided by 150. The calculated value for EK is negative 90.8 millivolts. Recall that we made the simplifying assumption that the membrane of a glial cell has only potassium channels and is therefore only permeable to potassium. This means that its resting membrane potential is exactly equal to the potassium equilibrium potential. Therefore, the resting membrane potential of a glial cell is negative 90.8 millivolts. It turns out that despite the fact that glial cells do have other types of ion channels besides potassium channels, the resting membrane potential of most glial cells is about negative 90 millivolts. Thus, a glial cell predominantly has potassium channels, and its resting membrane potential can be approximated with the Nernst equation. Next, let's explore how the resting membrane potential of a neuron is generated. The resting membrane potential of a typical neuron is about negative 65 millivolts, which is quite different from the equilibrium potential for potassium. How can we explain this discrepancy? One possibility is that the membrane of a neuron is also only permeable to potassium ions, but the ratio of extracellular to intracellular potassium is different, leading to a different resting membrane potential. It turns out that this is not the case. The ratio of extracellular to intracellular potassium is very similar in neurons and in glial cells. Another possibility is that the resting membrane potential of a neuron is dependent on other types of ions besides potassium. To investigate this possibility, let's compare the resting membrane potential of a neuron with the equilibrium potentials of two additional types of ions. Given normal extracellular and intracellular sodium concentrations for mammalian cells, the calculated value for the equilibrium potential for sodium is positive 60.6 millivolts. If we make the assumption that a cell has only sodium channels, then the resting membrane potential would be positive 60.6 millivolts. If we calculate the equilibrium potential for chloride, we find that it is negative 47 millivolts. Therefore, a cell with only chloride channels would have a resting membrane potential of negative 47 millivolts. As we saw earlier, a glial cell, which has predominantly potassium channels, has a resting membrane potential of about negative 90.8 millivolts. Note that the concentration values shown in the table here are for a generic mammalian cell. The ratio of extracellular to intracellular chloride varies quite a bit between different cell types. For this reason, the chloride equilibrium potential can vary over a wide range and may be as low as about negative 90 millivolts. Let's compare the equilibrium potentials we have found with the resting membrane potential of a typical neuron. The resting membrane potential of a typical neuron is negative 65 millivolts, which is different from the sodium, potassium, and chloride equilibrium potentials. The only potential candidate for a single ion that could explain the resting membrane potential of a neuron is chloride because, as I mentioned earlier, ECl can vary quite a bit between cell types. It turns out, however, that most cells, including neurons, have cell membranes that are permeable to all three types of ions. Therefore, for most cells, no single ion is responsible for determining the resting membrane potential. In order to calculate the resting membrane potential of a neuron, we need to take into account the relative permeabilities of the membrane to all three ions. If we assign potassium a relative permeability value of 100, then a typical value for sodium permeability would be 5, and a typical value for chloride permeability would be 10. The relative permeability values for potassium, sodium, and chloride vary quite a bit between different cell types. However, for most cells, the potassium permeability is greater than the chloride permeability, which in turn is greater than the sodium permeability. In order to calculate the resting membrane potential, we will use the Goldman-Hodgkin-Katz equation. The Goldman-Hodgkin-Katz equation takes into account the relative membrane permeabilities and the concentration gradients of more than one ion. For ions with a positive charge, such as potassium, sodium, the ion concentration outside of a cell is in the numerator, and the ion concentration inside of a cell is in the denominator. This situation is reversed for negative ions such as chloride. For a negative ion, the ion concentration inside of a cell is in the numerator, and the ion concentration outside of a cell is in the denominator. If we plug the values from the table shown here into the GHK equation, we find that the resting membrane potential of a neuron is negative 60.0 millivolts. Let's summarize what we have found. If a cell has a membrane that is permeable to only one type of ion, then the Nernst equation may be used to calculate V rest. However, if a cell has a membrane that is permeable to more than one type of ion, then the GHK equation must be used. The GHK equation takes into account the contribution of each type of ion to the resting membrane potential. This concludes part 1 of this video on the Goldman-Hodgkin-Katz equation. Thank you for watching.